Welcome back to our series on black holes. In part 3 we uncover even more mind-bending truths about these cosmic enigmas. We've journeyed far, from their gravitational embrace to the spaghettification of unfortunate matter, but the universe, in its infinite grandeur, always has more secrets to share, more veils to lift. Prepare yourselves, because today we venture into realms where the known laws of physics warp and bend, much like space-time itself around these celestial titans. We're not just talking about gravity anymore, we're talking about the very fabric of reality, the potential for connections that defy our everyday intuition, and the profound questions that arise when we stare into the darkest corners of the cosmos. Did you know black holes might be connected to wormholes? Imagine, if you will, a cosmic shortcut, a tunnel bored through the immense distances of space and perhaps even time itself. Could these gravitational behemoths, these points of no return, paradoxically be doorways? Or that some theories born from the fertile minds of physicists grappling with the deepest mysteries suggest they could be gateways to other universes? Think about that. Entire other realities, perhaps with different laws, different constants, different destinies, potentially accessible or at least hinted at by these enigmatic objects. The implications are staggering, challenging our very perception of what is and what could be. It's a journey that requires courage, the courage to question, to imagine, and to accept that the universe is far stranger and more wonderful than we can often comprehend. So, take a deep breath, clear your mind of preconceived notions, and join me, Alexander Bringadal, as we continue our exploration. Let's dive into these fascinating facts. The cosmos awaits, and its most profound puzzles are often hidden within its most extreme phenomena. We are but stardust, animated by curiosity, reaching out to understand the symphony of existence, and black holes are one of its most powerful, most resonant notes. Imagine the universe not as a static stage but as a dynamic, four-dimensional fabric, 3 dimensions of space, and one of time, all interwoven. This is space-time. Massive objects like stars and galaxies create dimples in this fabric, much like a bowling ball on a trampoline. A black hole, however, isn't just a dimple. It's an infinitely deep well, a puncture. The theory of general relativity, Einstein's masterpiece, allows for the possibility that these extreme distortions could, under certain conditions, connect to another region of space-time, or perhaps even another universe entirely. This theoretical connection is what we often call an Einstein-Rosen bridge, or more popularly, a wormhole. The idea is tantalizing. Could a black hole be one mouth of such a tunnel? Could you, hypothetically, enter a black hole in one part of the galaxy and emerge instantaneously light years away, or even in a different epoch? While the mathematics allows for their existence, the reality is far more complex. Most theoretical wormholes, if they exist, would be incredibly unstable, collapsing in an instant. They might require exotic forms of matter with negative mass energy density to hold them open, stuff that, as far as we know, doesn't exist or is purely hypothetical. Yet, the very possibility, rooted in our best understanding of gravity, compels us to explore. It's a cosmic what-if of the grandest scale. Building upon the mind-bending concept of wormholes, some theories take an even bolder leap, suggesting that black holes might not just be tunnels within our own universe, but potential gateways to entirely separate realities, parallel universes. Imagine an infinite cosmic ocean with each bubble representing a distinct universe, each with its own set of physical laws, its own history, its own unique tapestry of existence. Could black holes be the conduits, the interdimensional portholes linking these cosmic bubbles? This isn't just science fiction, it's a notion that arises from some interpretations of quantum mechanics and string theory, frameworks attempting to unify all fundamental forces. The idea often hinges on what happens at the singularity, that point of infinite density at the heart of a black hole. Perhaps instead of crushing everything into an infinitesimal point within our universe, the singularity acts as a seed for a new universe, branching off from our own. Or, in the many worlds interpretation of quantum mechanics, every quantum event creates a split into multiple universes. Perhaps black holes are regions where these splits become macroscopically significant or accessible. These are, of course, highly speculative frontiers of theoretical physics. We have no direct evidence, but the equations whisper possibilities, inviting us to ponder a cosmos far vaster and more diverse than the one we can directly observe. At the very center of a black hole lies a point that defies our current understanding of the universe, the singularity. According to Einstein's theory of general relativity, this is a region of zero volume and infinite density, where all the mass that has fallen into the black hole is crushed beyond comprehension. Imagine the entire mass of a star, or even millions of stars in the case of supermassive black holes, compressed into a space smaller than any subatomic particle we know. Here, space-time curvature becomes infinite. Gravity's pull reaches an ultimate, unbreakable extreme. It's a concept that strains the very limits of imagination and mathematics alike. The problem is, when we try to describe the singularity, our two pillars of modern physics, general relativity, which governs the large-scale universe and gravity, and quantum mechanics, which governs the small-scale world of particles and forces, collide head-on. General relativity predicts this point of infinite density, but quantum mechanics suggests that such infinity shouldn't exist in nature. There should be a fundamental graininess to reality at the smallest scales. This breakdown tells us that our theories are incomplete. The singularity is a signpost, pointing towards a deeper yet undiscovered theory of quantum gravity, one that can reconcile these two giants and unveil the true nature of reality at its most extreme. One of the most profound puzzles surrounding black holes is the information paradox. In physics, information isn't just data like your name or address. It refers to the precise quantum state of every particle, its position, momentum, spin, and so forth. A fundamental tenet of quantum mechanics is that information is always conserved. It can be scrambled, rearranged, or hidden, but never truly lost from the universe. However, when Stephen Hawking combined general relativity with quantum field theory, he discovered that black holes aren't entirely black. They emit a faint glow of radiation, now known as Hawking radiation, and over immense timescales, they can evaporate and disappear completely. So, what happens to the information of all the matter that fell into the black hole? If the black hole evaporates and the Hawking radiation it emits is purely thermal, random, as Hawking initially proposed, then the information seems to be irretrievably lost. This would violate the core principles of quantum mechanics. This paradox has perplexed physicists for decades, leading to intense debate and the proposal of numerous ingenious solutions. Perhaps the information is subtly encoded in the outgoing Hawking radiation, or maybe it's stored in some remnant, or perhaps our understanding of gravity or quantum mechanics at these extremes is fundamentally flawed. It's a high-stakes game, as the resolution could revolutionize our understanding of the universe's fundamental laws. To truly understand what transpires within a black hole, especially at its singularity, and to resolve mysteries like the information paradox, we need a theory that marries the macroscopic world of gravity with the microscopic realm of quantum mechanics. This is the domain of quantum gravity, and while a complete verified theory remains elusive, leading contenders like string theory and loop quantum gravity offer fascinating, albeit still theoretical, insights into quantum black holes. These theories attempt to paint a picture of what happens when gravity becomes incredibly strong on very small scales, precisely the conditions found within a black hole. String theory, for instance, proposes that fundamental particles are not point-like but tiny vibrating strings, and it suggests that black holes might have a fuzzball structure rather than a sharp singularity, resolving the information paradox by storing information on this fuzzy surface. Loop quantum gravity, on the other hand, quantizes spacetime itself, suggesting that there's a minimum possible area and volume, preventing the formation of an infinitely dense singularity. Instead, matter might bounce or tunnel into another region. These are frontiers of human thought, pushing the boundaries of mathematics and conceptualization, striving to listen to the quantum whispers emanating from these cosmic gravity wells, hoping to decode the ultimate laws of nature. We often think of black holes as purely destructive forces, cosmic vacuum cleaners devouring everything in their path. But the universe, in its intricate dance, reveals a more nuanced role. Supermassive black holes, millions to billions of times the mass of our Sun, reside at the hearts of most, if not all, large galaxies, including our own Milky Way. And it appears they are not just passive residents, they are active participants, cosmic architects influencing the birth, life, and evolution of their host galaxies. There's a fascinating interplay, a coevolution, between these behemoths and the star cities they inhabit. How do they exert such influence? When matter spirals into a supermassive black hole, it forms an accretion disk, a superheated swirling vortex of gas and dust. This disk can become so bright it outshines the entire galaxy, forming an active galactic nucleus or quasar. More importantly, these active black holes can launch powerful jets of particles and radiation, traveling at near light speed and generate immense winds. These outflows can sweep through the galaxy, compressing gas to trigger bursts of star formation in some regions, while in others they can blow gas away, quenching star formation. It's a delicate feedback loop, a cosmic thermostat that helps regulate the growth of galaxies over billions of years. For a long time, black holes were considered the ultimate prisons of the cosmos. Once something crossed the event horizon, it was thought to be lost forever, its light unable to escape. But in 1974, Stephen Hawking, through a brilliant combination of general relativity and quantum field theory, showed that black holes are not entirely black. They should, in fact, emit a faint thermal radiation, now famously known as Hawking radiation. This groundbreaking concept arose from considering the behavior of quantum fluctuations, pairs of virtual particles and antiparticles that constantly pop into and out of existence in the vacuum of space. Near the event horizon of a black hole, it's possible for one particle of such a pair to fall into the black hole, while the other escapes. To an outside observer, it appears as if the black hole has emitted a particle. For this to happen, the particle that falls in must have negative energy relative to an observer at infinity, effectively reducing the black hole's mass. This means that black holes are not eternal. They slowly evaporate over unimaginably vast timescales. For stellar mass black holes, this process is incredibly slow, far longer than the current age of the universe. But for hypothetical, very small black holes, the evaporation could be much faster, even explosive. This discovery fundamentally changed our perception of black holes, transforming them from simple gravitational traps into complex thermodynamic objects. Chapter 8. Echoes of the Dawn, the Enigma of Primordial Black Holes. When we think of black holes, we usually picture them as the end states of massive stars, collapsing under their own gravity after exhausting their nuclear fuel. These are the stellar mass black holes. But what if black holes could have formed much, much earlier, in the fiery crucible of the very early universe, long before the first stars even ignited? This is the intriguing hypothesis of primordial black holes. In the incredibly dense and turbulent conditions just moments after the Big Bang, even slight overdensities in certain regions could have had enough gravitational pull to collapse directly into black holes. These primordial black holes could span a vast range of masses, from much less than a gram, if quantum effects allow, up to thousands of solar masses. Unlike their stellar counterparts, their formation wouldn't depend on the life cycle of stars. If they exist, they could have profound implications. Smaller primordial black holes might have already evaporated due to Hawking radiation, potentially contributing to the cosmic background radiation, or even high-energy cosmic rays. Larger ones, if they formed in sufficient numbers, could even constitute a significant fraction or perhaps all of the mysterious dark matter that pervades the universe, holding galaxies and galaxy clusters together. The search for these ancient relics is an active area of research, a quest to find echoes from the dawn of time itself. Chapter 9. Tiny Terrors or Quantum Curiosities, Microscopic Black Holes. While we grapple with the immensity of supermassive black holes and the stellar mass remnants of giant stars, theoretical physics also allows for the mind-boggling possibility of microscopic black holes, objects with the mass of, say, a mountain or even less, compressed into a region smaller than an atomic nucleus. How could such tiny terrors form? One speculative avenue involves extremely high-energy particle collisions. While our current particle accelerators, like the Large Hadron Collider, haven't produced them, and are generally considered far too low in energy to do so under standard physics, some theories involving extraspatial dimensions predict that gravity might become much stronger at very small distances. If there are hidden, curled-up extra dimensions beyond the three we experience, it might be easier to concentrate enough energy to form a mini black hole than in a purely three-dimensional space. If such microscopic black holes were ever created, either naturally in the early universe or hypothetically in future, far more powerful experiments, they wouldn't be stable. According to Hawking's theory, the smaller the black hole, the hotter it is, and the faster it evaporates. A microscopic black hole would radiate away its mass in a burst of particles almost instantaneously. Detecting such an event would be a revolutionary discovery, not only confirming Hawking radiation but also potentially providing evidence for extra dimensions of space. Chapter 10. Cosmic Rumbles, Listening for Black Holes with Gravitational Waves. For centuries, our window to the universe was almost exclusively light, visible light, radio waves, X-rays, but black holes by their very nature are dark. They don't emit light in the conventional sense, so how can we see these invisible giants? In 2015, a new era of astronomy dawned with the first direct detection of gravitational waves, ripples in the fabric of spacetime itself, predicted by Einstein a century earlier. These waves are generated by the most cataclysmic events in the cosmos, such as the collision and merger of two black holes. Instruments like LIGO and Virgo are essentially cosmic microphones, listening for these faint rumbles from distant cosmic collisions. When two black holes spiral into each other and merge, they release an enormous amount of energy in the form of gravitational waves, distorting spacetime as they propagate across the universe. By detecting these incredibly subtle distortions, scientists can infer the masses of the merging black holes, their spins, and even test the predictions of general relativity in the strong field regime. This has opened up an entirely new way to study black holes, allowing us to observe events that are otherwise completely invisible. Each detection provides a new data point, helping us understand the population of black holes in the universe, how they form, how they grow, and their role in the cosmic ballet. It's like hearing the universe's symphony for the first time. And there you have it, 10 more glimpses into the bewildering, awe-inspiring nature of black holes. From potential portals through space-time and gateways to other universes, to the very breakdown of physics at singularities, and the ongoing quest to detect these cosmic phantoms through gravitational whispers, the journey into their depths is a journey into the heart of cosmic mystery. Each fact we uncover, each theory we propose, only deepens our appreciation for the complexity and grandeur of the universe we inhabit. It reminds us that there is so much more to learn, so many more veils to lift. Thanks for watching. If you enjoyed this video, and if your mind is still reeling from these cosmic revelations, don't forget to like, comment, and share. Let us know which fact blew your mind the most, or what questions still linger in your thoughts. Your engagement fuels our exploration and helps us bring these wonders of the cosmos to an ever wider audience. We are all fellow travelers on this spaceship Earth, and sharing knowledge is part of our collective voyage. Stay tuned for more episodes in our Black Hole series, where we continue to explore the mysteries of the universe. There are still uncharted territories, from the behavior of matter in extreme gravitational fields to the ultimate fate of black holes in the far future of the cosmos. The story of black holes is far from over. It's a story that's constantly being written by the universe itself, and by our relentless human curiosity. Until next time, keep looking up, keep wondering, keep questioning. The cosmos is calling.